welcome all. My name is Jari Savolainen. I'm a technical marketing for analog and MEMS in EMEA, coming from ST. Going to talk about biosensing for health and wellness monitoring. So first I'll give you some introduction about the biosensing as such, why we are doing that one. Then go a bit about the ECG, electrocardiography, some words about electroneurography, neural signals, and then electrooculography, that is the detecting of your eyes, showing a few things about ST new biosensors, and then the development tools. So why biosensing? So if you think about us humans, we are electric. So in our eyes we have optical image stabilization, for example. So if you look some kind of target and you walk towards the target, your eyes will be completely focused to that one. So you will be seeing crystal clear because of the stabilization in your eye muscles. And we have huge amount of nerves, and the nerve signals, they are electric. So if you think about hands and the sensing nerve ends in the hands, all signals are electric that go to the brains, giving the feeling of the object, for example. So this is the idea behind that why ST wants to measure the biosignals. So we have been doing plenty of other sensors previously, and now let's say the final thing is to contact to humans and detect the signals. And for example, in the heart, in our own hearts, we have a part that is making the signal, basically the oscillation of the heart muscle. So there's an oscillator and a pump inside us. So about ST, so we have been doing MEMS for over 20 years. Started with accelerometers, gyroscope, and IMUs over 20 years ago. So there's a natural path towards more intelligent edge processing sensors. A few years ago, we launched the machine learning core. So it's a pattern classifier in the sensors that can detect, for example, if you are walking or jogging or running, only inside the component. And further on, we introduced an intelligent sensor processing unit. So a processor that can do, for example, FFT or some other edge processing in the component itself. Then lately we have added infrared sensor to detect especially human presence, and finally biosensing late last year. So what are the challenges in the biosensors that we see? So if you want to have a wide high volume biosensing devices, you need to have multiple wellness parameters, and the sensing need to be non-invasive. So we don't want to have any needles or anything like that going through the skin. Sensors need to be very small size, very sensitive and low cost. They need to be accurate with high precision. Ultra low power consumption is always needed. If you have AR glasses or some heartbeat band or for example smart ring, you need to have very low power consumption. And finally, the data security is very important. So you're measuring the important feature of yourself. So you don't want to get them leaked anywhere. So the data security is also important. About the biopotentials and signals, what we are currently focusing on, it's heartbeat rate, ECG, respiration rate, for example. So with IMUs attached to your chest, you can measure the respiration rate. Then electroneurography, so especially the movement of the fingers that can be detected from the wrist. And electrooculography for the eye movements. So if you have VR or AR glasses, you can measure the the eye movements and the eyelid movements. So these are the focus areas at the moment, and finally we'll see the EEG, so the brain waves coming later on. Not yet. So I'll talk a bit about the ECG, because that is the obvious first application that we are looking for with these sensors. So if you think about the electrocardiogram theory, in the heartbeat you have separate cardiac cycles, P, G, R, S, T, and these segments and their variations are used for the diagnosis of your wellness and health in your heart. So the signal is up to 40 Hertz. So you need a bandwidth at least 80 Hertz, and more is better. So maybe 150 is recommended. So then you can catch all the fine signals that are in the ECG. But the problem is that the ECG is only in a millivolt range. So if you think about, you need to measure something on your body. For example, in our demo booth, we have a demo with only touching your 4 fingers. You can measure this millivolt signal that is based on your heart. So this is the theory, and you have been seeing already in the market a lot of these PPG products. So majority of the smart watches or smart rings, they use the optical method called PPG. So these two methods are measuring the heartbeat, but with ECG you can get to this very fine, precise segments of the cycle. So they can be, for example, in the same product, and they complement each other. And using the PPG and ECG, you can measure the heart, the blood pressure. So this kind of combination can even do the biosensing better. PPG is an active mode, so you send a signal to the vein, and you measure the volume change in the veins, the actual blood moving in the veins, and then you have a receiver to measure the reflectance. So in a way, PPG consumes more power, since in ECG we have only very high precision analog front end, let's say passively measuring the signals we are producing. Just a comparison chart, and maybe the only big difference between the measuring principle is that you need 2 different contacts in ECG. So you need to measure over the heart. In PPG, the optical method, you can measure only with one point. So of course that's a benefit for the heartbeat, but you lose the high accuracy of the heartbeat variability. So just to give this kind of overall summary of the 2 technologies that can be used. Okay, then how do we think about the context aware? What does it mean in our context? We combine accelerometer and the analog front end in the same component. So if a person is moving a lot, they might have a chest band measuring the ECG, and if you are jumping and going around, the signal might be really bad. So the accelerometer can be used to discard the bad ECG measurements, and they are in the same component, measured all the time, in the same place, same time. In addition, the way that we are making the accelerometer, it has the machine learning core inside. So the customer can detect, for example, if the person is walking, standing still, or running. So if you want to make a product that measures the ECG only when you are standing still, and then the reading is really good, then it's possible to use only the accelerometer plus the biosensor module to make the decision to, for example, wake up the MCU. So that's the context-aware ECG. We are capable of following the human movement only in the sensor level, and then make an interrupt and wake up the MCU. So, for example, the artifact removal is one of the key things. For example, if you breathe a lot, it might have this kind of very low frequency drift in the signal. If you move a lot, there is more high frequency muscle-based noise in the signals. So it's then up to the application level decision making that how much you want to filter out certain artifacts. Do they mess the measurement, for example, completely, or just give a bit unreliable data? So the machine learning core inside, what I said, it's added. This is not showing too well, but it's added to most of the motion sensors we have. So in our world, the biosensors, they are motion sensor having biosensing capabilities. So you can use the same machine learning core stuff that is available in most of our accelerometers, IMUs in the components. So the machine learning core is better for pattern detection, for example, as I explained, walking, jogging, running. So you can only detect this in a small component and then give the already processed data to the MCU. The component has also, and our components typically, they have a finite state machine for more this kind of event-based gestures like flips and taps and double taps and so on. So there's these two embedded processing inside the component. Some application examples of the ECG. So for example, the smartwatch example is maybe the most obvious, that if we want to get the technology out in the masses. So you would have a wrist device, the other electrode would touch your wrist, and then you would close the loop with the other hand. So this means, of course, that you cannot run during the measurement, but you can get very high accurate variability data, for example, if you stop while you're exercising. So this is one example. Then we have a collaboration with a company called DuPont, and they made this kind of heartbeat and wellness patch. It's basically a heartbeat band without the band, so it's glued to your skin. But anyway, this is one example of. Then you get really close to the heart, and you can actually measure the physical movement of the heart with the accelerometer. So you can see from the animation there that the SCG is the actual movement of your heart when it's pumping, and ECG is the electrical signal. So when you go close to the heart, you can get the both with our component. Then another example of ECG, one company made a demo of a car wheel. So when you have the hands on the car wheel, you can detect the wellness of the driver and basically the attachment of the hands as well. So those two things in the same time. So you can see the applications for the ECG only is very wide, and there's many more to come. So it can be measured, as I said, from the smart ring. So we have some demos on that one already, with the same principle like the smartwatch, and so on. So okay, let's move on to the next application level, because this ECG is only one that we can do. The next one is electroneurography. So with the same analog front-end we are using and producing, we can measure the neural signals coming from your brain through your hand to the fingers. So the idea here is to detect the intention, not the movement. So there's a company called Python that is making let's say development on this area for a long time, and collaboration with ST, they made a device that can detect the neural signals. So when you intend to move the finger, for example, you get the signal before you see the actual movement, and this is, for example, giving you possibility to make gestures So you detect the neural signals from the wrist, and then you can, for example, in VR or AR world, you can generate gestures without any actual real big movement. And if you move your hand, for example, with the other hand, there's no signal at all. So it has to be your own intention and own neural signal, and that's already in a phase that there is a demo device that is shown in some of the conferences already. So I'll move forward to some of the example gestures that you can detect. So this kind of pointing, index pointing, then connecting your fingers together and so on. So all of these can be separated from the, I would say, pretty messy neural signals. So you can imagine that the ECG is a big signal compared to these ones. And then you have the EEG, the brain waves, and that's even lower. So to achieve this, you have to do a lot of research and filtering and AI and so on to get to this level. So more news on this collaboration later this year. About the electrooculography, so this is then for the eye movement. So if you put the electrodes, for example, here to your nose, you can detect the eye blinking and the moving of the eyeballs. So in the eye you have a positive cornea and negative retina. So the eyeball is having different charge. So moving the eyeballs has an effect to the signal as well as the blinking. So this is of course quite obvious to use in an AR class or VR class. So in a way, in a summary, our idea of the biosensing is pretty wide, and there's many other things that you could try. So basically, anywhere you move your muscles or there's a nerve going, you can catch the signal if you have electrodes close enough and good algorithms. Okay, let's go to the components that we have now to provide. So the components, they have all inside MEMS element. So there is two parts. One of them has accelerometer, the other one has accelerometer and gyroscope. And then we have a very high precision and high sensitivity analog front end. Then we have AD conversion, of course, and then the embedded machine learning and finite state machine. So this is the structure of the components we are bringing. And if you think about the end signals, then so we bring the raw, let's say, analog front-end signal out of the component. We are bringing a library. It's available already to measure the ECG. But then for the neurography, electroneurography, and oculography, at the moment, let's say customers need to do their own software. But there is a big development ongoing at the moment in this field. The ECG is the one obvious that we can provide some help for you, but then the other ones, they are a bit more complicated and application related. So then it's more like customer to make their own algorithms and code. So how we differ from the general purpose analog front end. So typically many suppliers have analog front ends and they can be bigger in size. They typically have multi-purpose, so you can use them for many purposes. So our focus is on the human signals, not all that the analog front end can do. We add the motion sensor to the same package, so it's very small. So if you use a general purpose analog front end, you want to, for example, measure step counting or whatever, you need to add some MEMS component next to it. So these kind of differences there are. Typically the analog front ends out there are more expensive actually than our component, and typically in the analog front end that is standalone. You need a quite powerful MCU next to it. So there's plenty of pros and cons. So if you only measure certain biosignals, our component is very small, cost effective. And if you want to go basically whatever and do very high precision, for example, EEG at the moment, you might need to have a even more sensitive device. So that's the difference. This is the part number we are currently having. So ST1 vAFE3BX, super easy to remember. The power consumption 50 microamps. There is a configurable input impedance, so you can fine tune it a bit from 100 mega to 1 giga. Its noise level is low enough for these neural signals and ECG. 2x2 packets, very compact. No need of any pre-amplification, so it's quite easy to use at the moment. The other component here is having the IMU inside. It has slightly less sensitivity, so you need the op-amp in front of it. So I would recommend only to use when you really need a gyroscope as well. The library we provide is called BioVSM. So this gives out different kind of heart rate and heartbeat indexes. So you have a variability index between the peaks, the actual heartbeat, standard deviation of the peaks, and so on. So basically, this library is running in STM32. You connect our component to it, put two pads out from the component, for example, to the fingers or over your heart, and then you get to the application, this kind of high-level heart wellness signals. It looks something like this. So you get there's a lead of detection, for example. So that's quite convenient. So if you have some kind of product that is touching your skin, it's good to know that when one of the lead is off, you get the heartbeat rate, maximum, minimum, root mean square of the differences, and so on. So it's a full-blown library, free to use if you select our component and our MCU. Okay, then about the development tools. So we are bringing this kind of tools at the moment. So by the way, welcome to the stand where we are to test the demo. So there is typical development kit is this kind of professional MEMS tool. It's called Steval MKI 109D. You connect the board, the smaller board with the electrodes to that one, and then you can connect the motherboard to PC. And that's the main way to make your own experiments in the companies and some algorithms on top of the raw data. There's another version that you can connect this kind of ECG cable, so a 3.5 millimeter audio plug. So then you can connect, for example, the electrodes to your nose or to your, I don't know where, to your wrist or anywhere. So this is the setup that we currently have. So you have a graphical interface called MEMS Studio and the PC. You can connect the MEMS tool to it. You can get the raw data out. You can save the raw data and maybe do some analysis later on in the analysis tool. Maybe run some AI algorithm in your own environment. So that's available now and that's about it. So thanks for your time. There's some minutes of questions. So if you have any questions, I can ask. You can reply. Please. Yeah, there was behind you.
Hi, my name is Peter from Hey Salad. We're developing a bunch of products, specifically a smart ring. And the biggest challenge has been if we're going to apply like specific chips that use AI, let's say our ARM Cortex, there's going to be a lot of heating. Have you come across any companies that have solved this problem to reduce the heating on edge AI devices?
So of course it depends on the amount of data you need to calculate. So our as I said, the machine learning core is a pattern detection. So certain kind of things you can do already in the component, and that's really low power. It takes from 5 to 10 microamps only, but then it's only like pattern detection. Nothing. It don't learn on the fly, for example. So then we have another component category with sensor processing inside the sensor. So that is a RISC-based 32-bit 10 megahertz processor, and that is also pretty low power. So you can do plenty of things like anomaly detection on that one. So if you have some kind of machine and the gear is wearing out, there is a demo in our booth as well. So you can detect, for example, that kind of things inside the component in few tens of microamps. But then you're right, if you go even further in the chain to the big MCUs and for example, digest camera video image or something like that. Yeah, then I don't know. We have some neural network processors coming, so probably they have a better influence than on the power consumption. Yeah.